Hey everyone, and welcome back to the Data Idol Summer School. I'm Amy and I'm the Senior Events Coordinator for the Data Science Festival. The purpose of the summer school is for people that are transitioning into data or just kickstarting their career. We have around 40 sessions running from August to October, which you can watch along with the community. We also have a Slack channel that you can join, and we'll be popping the link to join this into the chat. If you prefer to watch the sessions in your own time, this will also be an option from September onwards. I'd love to say a huge thank you to all of our summer school partners that have made summer school a reality this year. I'd also love to say a huge thank you to our speakers who have given up their time to support the data science community. I'd love to now introduce Chanuki, who will be presenting her talk, Intro to Computer Vision. Thank you for everyone's support, and we hope you enjoyed this session.
Welcome to the Introduction to Computer Vision course with Convolutional Neural Networks. I hope you enjoyed this course. We'll get started. So just to cover what we're going to talk about today, I'm going to first introduce what is a convolutional neural network. Then I'll have a first exercise, which we'll go through. Then there's going to be a second part where I'll introduce you to transfer learning. And then there'll be a second exercise. So let's get started. So when do we use convolutional neural networks? Well, obviously the most common example is autonomous vehicles. So if they want to figure out where they should go on the street and how they should stop, then the vehicles themselves are using object recognition. And this is where convolutional neural networks really excel. So they'll, so this is a really great example where it's like, ooh, that's a traffic light, that's a person, that's a car, that's a truck. And but I wanted to talk to you about how we use convolutional neural networks here at Culture Trip. So one of the things we work on all the time is recommending hotels to people. And we need to figure out which hotels are actually good quality. And one of the ways actually of looking at the quality of a hotel, of course, is by the ratings people give a certain hotel. But sometimes we don't actually have enough ratings, or it could be a new hotel. So we also need to figure out in these instances how we might get another signal of the quality. And a really interesting way we can kind of infer it to a certain degree is just by looking at the images. And you can imagine that higher quality hotels will have higher quality images. So one of the things we can use is Google's neural image assessment, convolutional neural network that's already been trained to recognize, quality, and then use that neural network to assign an overall quality to a hotel. And we can use that for a signal when we don't sometimes have the data that we would like to have. Another example is to come up with hotels that are similar to each other. So we don't always have great metadata on our hotels, and it's even if we do have metadata on our hotels, they don't really give a feeling about how likely the hotels are to each other because there might be more practical information. So another way of extracting more information, of course, again, is the images of the hotels. So we can train it to recognize things that maybe Culture Trip cares about. So one of the things we might really care about is if the hotel has got creative design, because that might be something our clients are interested in. So if one hotel has a creative design, but it's not available, we can suggest another hotel that's also got a creative design. Another example of a tag is boutique. So if a client is interested in a boutique hotel and the specific one is not available, we can use this image tag to find other boutique hotels nearby. So there's just a couple of examples of how convolutional neural networks actually help us with our work. So why do we need convolutional neural networks? Well, they're a little bit different than neural networks, and mainly, how do computers look at images? Well, they see the images as a matrix of pixel values, but the problem with with images is that they have 3 channels of colors. So, if it was one channel, it would be black and white and it wouldn't be a problem. But because there's 3 channels, if we have a 640 by 640 image, then the 640 times 640 times 3 will end up being a neural network with like 1.2 million weights. So we have to kind of be very efficient with how we actually train a neural network. So that's why we use convolutions. So similar to regular neural networks, CNNs have multiple hidden layers. And unlike regular neural networks, the layers of CNNs have neurons arranged in the 3 dimensions. So this is like width, height, and depth. So it was like the example I explained before, where we got 640 by 640, because that will be the size in the image, times 3, which is the depth of the 3 channels. So in the past, convolutions are kind of an they are an old concept. So in the past, what we would do is we would pick our filters to apply to images. And they're very common filters. People, really spend a lot of time trying to figure out what's the best one. So these filters might actually help with something called edge detection, for example. And that's what a convolutional layer really is. It's just trying to find how do we filter out, add filters to our image to help make sense out of that image computationally. So the great thing about convolutional layers is that they allow neurons in a layer to only be connected to a small region. So this drastically reduces the parameters we need to train, as each filter will share the same weights and biases. So similar to a regular neural network, each neuron in a convolutional neural layer is connected to a nonlinear activation function and a bias term. But the main difference is that if we have a fully connected network, then we're going to have millions and millions of parameters. It's just not going to be efficient to run. But because convolutional neural networks, convolutional layers specifically, are connected only a small region, we don't have as many weights that we need to train. So one important feature of a convolution is padding. So every time we apply a convolution, the resulting matrix becomes smaller as it loses a border. So this is an example here in the animation. And unfortunately, that means your image will continue to shrink until it becomes really tiny. But we don't want to lose the image, the edges of an image, because that's really important. So one of the solutions is to include padding. So you will often see in a convolutional layer that there's it says, what kind of padding do you want? Very common type of padding is to introduce a zero border around. And so convolution, then it's done as normal, but the result will now produce an image that is of equal size to the original. Stride is another technique that is important to use. The stride is the size of the step. The convolutional filter moves each time. So a stride of 1 will only move it just 1 pixel at a time. By increasing the stride, your filter is sliding over the input with a larger interval and thus has less overlap between the cells. So you can kind of play around with it to see, what actually, does it need a lot of detail, or can you start skipping and just kind of get a rough idea of your neural network? And of course, commonly, just like standard neural networks, it is common to apply a nonlinear activation function on the outputs of the convolutional layer. A very common one is ReLU, and is the most common nonlinear activation function. It's a computationally less computationally expensive. You can train it faster, and ReLU just gives an output of X if X is positive, otherwise it's just 0. So just a few more details with the neural networks before you put it all together. Another thing we want to do is there's pooling layers in the convolutional neural networks. So pooling layers help reduce the size of the representation, and that can help speed computation. A very common way of pooling is by max pooling. So you just basically take the maximum from each kernel. So putting it all together now, here is like an example of a convolutional neural network. And so you've got your input coming through, you've got your convolution layers, you've got your activation functions of the ReLU, and then you've got the pooling layers, and then you might have more convolutions, ReLU, pooling, etc. There are many, many different ways of building these convolutional neural networks. And finally, at the end, you'll flatten everything, and then you'll have a few fully connected layers as well. So this is a very common classic example. And what the convolutional neural network is actually doing is it's pattern seeking. So basically it's learning maybe how to recognize lines and loops when it comes to numbers, or it could be looking at features when it comes to trying to recognize a face. So again, just to summarize the different layers that go into a CNN. So you've got your input, which is the raw pixel values of the image in RGB. Then you've got your convolutional layers that compute the output of neurons that are connected to the local regions in the input. Then you've got your ReLU, your activation function. You've got your pooling layer, which perform a downsampling operation. You've got your fully connected layer. So these are like normal neural networks where each neuron in a layer is connected to all the neurons in the previous layer. And then you have your final output layer. Very typical for classification is to have a softmax layer. And that a softmax would compute a probability that an input belongs to a certain class. And you can have several classes. So it could be binary, or it could be, several classes, even like over 1,000 if you wanted to. Yes. So last bit of detail, of course, training CNNs. So of course, just like neural networks, you have to apply a loss function. So the two classic loss functions you can have are mean squared error, which is really common. And for classification, you commonly use binary cross entropy loss. We need to optimize our algorithm. Very classic one we could use is stochastic gradient descent, where we give it a small subset of the training data and you choose the size of the step or the learning rate. And obviously you move in a direction where you're trying to reduce the cost function, so it converges when it flattens or it reaches a minimum. Some other algorithms that you can also use that are really common one is RMS prop. RMS prop divides a learning rate by an exponentially decaying average of squared gradients. Momentum is typically added to a stochastic gradient descent. So you can, that way it can progress faster by adding a temporal term into your learning rate. Atom is a combination of RMS prop and momentum. And so the update rule combines an exponential decaying rate of the past squared gradients, which is the RMS prop, as well as its past gradient. It's also applying the momentum as well. And then NADM is also a variant of Atom that incorporates Nesterov momentum. These are just some common optimization functions. There might be more as well that just constantly get introduced. Finally, you need to tune your hyperparameters. There's quite a lot of hyperparameters that you need to tune. And when you're tuning your hyperparameters for a convolutional neural network, it's faster if you actually just look for random combinations rather than doing a grid search, because there's just so many different combinations and you need to kind of go through the combinations fast. So one of the things is you need to figure out how big your batch size is. So these are the mini batch sizes. You're giving like a batch of images to train for your neural network to train. Then, how many epochs do you want it to run? So one forward pass and one backward pass of all the training samples is one epoch. So you have to figure out what learning rate you want. So if it's too low, then training can be more reliable, but optimization can take too long as the steps towards a minimum of the loss function are tiny. And if it's too high, your training may never converge, might even diverge, and the weight changes that can be so big that the optimizer overshoots the minimum and makes the loss worse. So from typical experience, the learning rate can be between 0.01 to 0.0001. And initially, you can basically just add an extra zero and you can kind of use that to quickly understand where it might converge. And then normally you should be able to find, if your neural network is able to train or not pretty fast. So some more details on the training. So typically you split your data set into 60% training, 20% dev, and 20% test. So you keep your test set aside while you're doing everything else because you don't want to touch your test set. And there's a lot of you'll start going internally quite a lot, especially with the hyperparameter search. So always keep this test set aside. So it's really important to keep 3 folds. And so make sure your train, dev, test do not share the same samples. Obviously ensure they all have the same distribution. And you use your dev set to pick the best parameters for your model. And then, of course, you only use your test set in the very end to see how your model is working. But for simplicity on this exercise that I'm about to run you through, we're only going to have a train and a test set. So a typical training procedure for a neural network. So you load your train, dev, test image data sets. You define the hyperparameters. You define the CNN architecture. You set the optimizer, such as stochastic gradient descent and a loss function. You train the network using an optimizer over a set number of epochs. And then finally, you test accuracy. Okay, so I think this is going to be easier to seeing how it actually works in real life. So we're going to start coding now. Okay, so we're now going to go through an exercise, and you can get to that by typing in the URL that's in the slides. And it'll open up this notebook in Google Colab, which is free to use. And we even get to use a GPU for free, which is really great. So you want to double check and you want to run this code to begin with and just see that it types out GPU device found. Because if it doesn't, what you want to do is you want to go into runtime and when you change your runtime type and make sure that GPU is selected. So let's get started. So I'm not going to run this on the course right now with the recording because it'll take a few minutes and it'll be a bit of a lag, but I'll talk you through the code. So as I said before, you want to run these first lines. You just want to make sure that we definitely found a GPU. And we're going to first take a look at this data set. So this is the C410 data set, very common data set to use just to get your head around how to use convolutional neural networks. And there's so basically the data set is labeled with a few different categories that are just like airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And what we're going to do is we're going to build a convolutional neural network to actually predict what the category of this image is. So let's build a simple sequential model. So this is the code that would be used to build a sequential model. And it might look a little bit scary at first, but it's everything we already talked about. So here is your input. So again, and then it's going to take in the height, width, and the depth that we would have set. And then we're adding our convolutional neural net layers here. And you see the activations of ReLU, which we discussed. We want to do max pooling, and these are these layers here, which is this, the max pooling 2D. And then finally, we want to flatten everything up, which is just what it's doing there. And then we want to add one fully connected layer. It's called dense for whatever reason. And then we want to have a final activation layer, which is a softmax, which then outputs a prediction of one of the 10 categories. So if we type out the model, then these are the layers that are going to be coming across, and it tells you how many parameters that we're actually training, and it's 66,000 parameters. So quite a lot already, just for a really small network. So we want to prepare the data for training. It's very common to scale the data to the range of 0 and 1. And we want to convert the labels into integers just to make training easy to do. One thing that's common that we use in TensorFlow is Keras in TensorFlow is the image generator. And what we can do is when we load the images into the image generator, we can already start to add a little bit of augmentation into the data. So it's very important to add augmentation to images because we want to make the neural network as versatile as possible. So we don't want it just to recognize cat in exactly the same pose as, all the time. So we're going to be changing the image a little bit by giving it a bit of a rotation, zooming it in and out, and then it starts to see the same image in different types of forms. And then it becomes more versatile to actually recognize it again. So this is really important to do. Now we're just setting up our parameters to train the neural network, which is a learning rate, which is here. We want to give it 128 samples at a time. We want to train it over 5 epochs. So that's like running through the entire data set. So it's going to do it over 5 times, but it's going to be augmenting the data every time. So it's going to see something a little bit different every time. We've got SGD, stochastic gradient descent, as our optimizer, and we've given it momentum of 0.9. We've given it a categorical cross entropy loss function, because that is what we normally use if we've got multiple categories. And our metric is just accuracy. And then we're just going to train our neural network here by fitting everything. And we're just going to run it. So I've already run this, and it's ran over 5 times. And you can see that the validation accuracy is getting higher and higher, and our loss is going down. So it's doing a good job. And all I've done here is I've basically plotted the training loss and the accuracy. So it's just obvious to see that training loss is decreasing and accuracy is increasing. And then finally, I've just run a classification report on the predictions on the test set. And it looks like overall, we get an accuracy of about 35%. So if we load the images, we can see how it's doing. And for the most part, it's doing okay. It guessed airplane, frog, but it got confused with the dog. So it's a dog, not a horse. And then again, a bird, not airplane. And you can kind of see why I got those things a little bit confused. So part of this exercise for you now is just to have fun and just play around and just change all you need to go back is change some of the parameters. So you can, change the optimizer to atom or natum. You can change the epochs. You can change the learning rate. You can change the batch size. Or you can be really creative and actually change the convolutional network itself. So just basically, I'll just go through and show you. So here is, if you want to become brave, you can actually change the convolutional neural network yourself. But otherwise, what you could do is just try changing these different parameters here, different learning rate, batch size, or epochs, or you can set up different optimizers and change, maybe change the momentum. So you can just, play around in a simple way or play around in a more complicated way and just use this notebook to try to get around how convolutional neural networks work. So that's it for the exercise. So we're going to now that you've finished the exercise, we're going to now move on into talking a little bit more about convolutional neural networks. And I'm going to start introducing transfer learning. But before that, I wanted to just go over a history of convolutional neural networks and introduce you to ImageNet, because ImageNet is something you must know when you're working with CNN. So ImageNet was originally built because they recognized that we needed to have a label database to help content-based image search and image understanding algorithms. So it's basically has about 14 million images that have been manually labeled into one of 20,000 categories. So it's based on the word net hierarchy. So you've got things like many different types of dogs, for example. I'm not really sure why they picked that, but I mean, the categories in ImageNet are a little bit odd, but they are really great for training your base neural network, which you'll use later for transfer learning. But ImageNet has been such a great database. It's also been used to look at how neural networks kind of have fared over time. So yes, it's always a benchmark for how well image classification algorithms fare. So as you see, in 2012, we had AlexNet is one of our first neural networks. So so AlexNet was famous. That was the first time a model performed so well on the ImageNet large-scale visual recognition challenge. So it really convinced people that deep learning could work in computer vision. It introduced the ReLU activation function, the use of the ReLU activation function. And just a little side note that the image above shows the neural network split into two, as they had to train over 2 GPUs, because at the time they didn't have a neural network a GPU that could actually train a whole AlexNet. Ironically, now AlexNet is such a small model that it's actually very easy to train these days, and we don't really use AlexNet anymore. But just wanted to introduce it because it was like the one of the momentous moments where it was finally like, wow, deep learning really works for images. Another one, which is also old, but we actually still can use it because it does generalize well, and that's the Visual Geometry Group, VGG by Oxford. This was a 19-layer, it's still a very simple CNN. So it's got smaller filters, like 3 by 3 with a stride of 1, the same padding, and max pool layers with 2 by 2 with a stride of 2. So the spatial size is decreasing while the depth is increasing, and it's going a little bit deeper than AlexNet, but not much, it's only 19 layers. So Google Inception model was another huge breakthrough, and you'll see different types of, some of these Google models now that are used quite a lot. But the key contribution with Google's Inception module is that it was basically reducing bottlenecks. So there's this parallel combination of 1 by 1, 3 by 3, 5 by 5 convolutional filters, but the use of the 1 by 1 convolution blocks was there to reduce the number of features before the expensive parallel blocks. So these bottleneck layers allow for larger savings in computational cost. And then we've got ResNet, and this is like 152 layers, right? Remember, AlexNet only had 8, now we're going to 152. But in general, deeper models are harder to optimize. So Microsoft, Resonance is Microsoft ResNet, and they introduced the concept of a residual block. So using layers to fit a residual mapping, which is like just a shortcut. And they, did incredibly well. And in fact, you'll see different versions of ResNet now used today. So I'm going to introduce you to transfer learning, and I'm going to go over a paper that I actually did a long time ago. So it says 2017, but actually this work was done in 2015, so it was a while back now, because it takes a while to publish papers in general. And so this is my first time using transfer learning. So in this one, I basically wanted to understand, I wanted to train a neural network to see if they could understand the beauty of images. So my training data came from this website called scenicness, where you rate these images between 1 and 10. And I had about 1.5 million votes for 217,000 images. So, and my kind of what I wanted to do is, can we predict the scenicness for new images? So what I did was use transfer learning. So I use a pre-trained convolutional neural network that was already trained on a Places 365 dataset. Now the Places 365 dataset is just good at recognizing places. So where ImageNet was more about image categories, Places is more about place categories. And when you do transfer learning, what you're doing is basically you're training a convolutional neural network that already knows how to do something a little bit different. So this time I'm asking the neural network to, as opposed to predict the place category, I want it to guess how beautiful it is instead. So give it a scenic score. And it did really well. So we got a correlation of 66%, which is interesting because you're never going to get 100% to 100% predicting beauty. I don't think anybody can even do that. So 66% is quite good for this type of exercise. So I wanted to see how my neural network actually did with places around London. So Hampstead Heath is one of the places that I would often, go for walks, especially during lockdown. And that was like only fun thing you could do. And Hampstead Heath is a really beautiful area. So I wanted to know if my neural network can actually guess, how, beautiful is Hampstead Heath. So every dot here represents an image that from another website called Geograph, where people are just like uploading documentary images of a certain area. And the gray dots are not scenic, and the green dots are scenic, and purple are very, very scenic. And you'll see all around Hampstead Heath that there's a lot of green and purple dots. So this neural network is actually starting to recognize that this is a beautiful spot, and it picks these images, for example. If we look at images around London, we'll notice that parks come up with like green and purple dots, and there's an interesting path on this kind of map. And then I was wondering what it was, and turns out it's Regent's Canal. So it's really good at kind of picking up different parts of London as well. And interestingly, it's also picking up on the fact that we do find built-up features as beautiful. So here is Tower Hill, like very beautiful characteristic building, and it's rated all that as being scenic. So how do you do transfer learning? So what you do is you choose your pre-trained model. So I use Places, but a lot of people will just start with standard ImageNet. In fact, always start with ImageNet because it's really versatile, even if you're using satellite images. And even though ImageNet has been trained on different types of images, it's just such a big database that the neural networks that are trained on it work really well. So what you do is then you take your model and you just need to adjust this. You want to change your last layer to, as opposed to predicting, say, this is places. So as opposed to asking the neural network to predict places, I had to change the last layer to instead predict the scenic score instead. Then you want to train it on many, many different networks. So remember before I was introducing these different networks like AlexNet, VGG, GoogleNet, ResNet. Well, there are different versions that you can now train just using they're all already available in Keras that is in TensorFlow, and these are the different models that you can use. But as usual, it's always easier to see it when we're coding. So we're going to move to coding exercise again. Okay, so we have another notebook, and this is also in Google Colab. And so don't forget to make sure that it's running on a GPU. And if it's not running on a GPU, you can change your runtime type, because you're going to need that definitely for transfer learning. So we load our libraries that we need, and this is just code just to load the images. So we're going to use the images I actually used in my paper. But I'm just going to simplify the exercise. As opposed to predicting a rating, we're just going to predict whether it's scenic or not scenic. So high or low. So again, we want to set up a parameters for training. So, we're setting our image width and height to be 128. That's a classic size we might use for convolutional neural network. We're saying, if it wants to run over 5 epochs, we're giving it a batch size of 32. We're choosing a very simple optimizer, stochastic gradient descent. We're choosing a learning rate of 0.0001. So one of the things you can do is fine tuning. So that is tuning a pre-existing model to perform a different data set and a task. So that is one of the easiest, one of the ways you do transfer learning. But you can also turn fine tuning off. And then when you do that, it will basically keep all the weight static, but it will only do the last fully connected layer. So it's interesting. So if you want to use fine tuning, if your task is quite different, so, and if your images are different. So if you want to do object kind of classification and you change it, and it's on ImageNet, then you might not want to do fine tuning because it's a very simple task. It's very simple, like similar to your images that you're using. But this exercise, I noticed fine tuning works better because we're not doing object recognition here. We're training over ImageNet, but we're asking it to look at the scene instead. So you have to kind of play around with it, and then you get an understanding of whether you want to use fine tuning or not. So again, we're using our image data generator, and this is where we're augmenting our images as we're loading them in. So allowing it to rescale, rotate, shift it, flip it if it needs to. And then we're also setting up our train generator and validation generator. And I'm using flow from directory, but you can also use flow from dataset. If you have a dataset and you have a folder of images, you can use that as well. But this time we're just using flow from directory. So got some code again to examine our dataset. And you can see these are low, not so scenic images, highly scenic images, and not so scenic images on the bottom, and a few high images. And you'll see this is going through the image generator, so it's kind of flipping it, it's changing it a little bit, and this is what the neural network is going to use to learn. Finally, these are just some functions just to help our neural network be able to do fine tuning. So one of these things is trying to figure out where from where you want to freeze your weights or not. So if we look at the inner workings of the model, we basically reload ImageNet, and then what we want to do is we want to flatten it, and then we want to introduce some fully connected layers. So we've got our ReLU, and then we're going to do a sigmoid function just to predict, if it's a probability, but we want to cap that 1, so between 0 and 1. We set up our optimizer here. And this is again where we're training our algorithm. So we're just fitting our algorithm, based on all these parameters that we've already set up. And yeah, the sum to loss function is binary cross entropy because it's we're just predicting 2 categories. So highly scenic or low, not so scenic. So I've already trained it over 5 epochs. And as you see, again, the accuracy is increasing, the loss is decreasing. We've got this plot here, and it's doing really well. We've already got a 91% accuracy. And the reason we are getting a much higher accuracy here than we did before is because we're doing transfer learning. So transfer learning helps you kind of get to good results really fast. So you almost always want to use transfer learning because when you're transfer learning, you're teaching a neural network that's already knows how to do something, just something a little bit different. So you should see accuracy improve fast if it's a problem that a neural network can actually deal with. So here's the algorithm, and it's only got a couple of things wrong, but it knows already that these kind of city industrial pictures are not that beautiful. So it's predicted those as low, and it's predicted the other images that are a bit more natural as highly scenic. So it's already done a really good job in a very small amount of time. If you run this notebook, it should only actually take a few minutes. And that's the end of the exercise. So we finished our last exercise, and I just want to leave you with a few further resources so you can keep learning. So a really great course just to kind of understand the basics of convolutional neural networks and the kind of theory behind it is the Stanford's Convolutional Neural Networks course. A course just to learn practically how to use convolutional neural networks is obviously Andrew Ng's deep learning courses are amazing. There's one very specifically on convolutional neural networks, so that's one to just understand practically how to use it. If you want to, so we've used Keras and TensorFlow in these exercises, and this is the URL just to learn a little bit more about Keras and what you can do. And then finally, we have a deep learning computer vision practitioners community. So this is where have academics and commercial practitioners getting together and basically talking about some of their projects. So if you do actually really get into convolutional neural networks, then please visit our community, and you can have a look and see if you want to, come along to one of our events. We've paused them temporarily right now, but I'm hoping as soon as you start watching these videos, we'll be meeting up in real life again. So hope to see you at one of these events in the future. So have fun working with convolutional neural networks. So that's a wrap. So I hope to see you maybe at one of our future events that we run, or just have a great time working with convolutional neural networks. Thank you.